Hello everyone, myself Yadagiri, Assistant Professor, Department of Electrical and Electronics Engineering, and also I'm the Faculty of Basic Electrical Engineering from the Department of EEE, MLR Institute of Technology, Hyderabad. In the last session, we have discussed about the different powers in electrical circuits, AC circuits, and also the power factor as well as importance of the power factor. So in this session, we are going to discuss about the analysis of the pure resistive network with the help of an alternating source. So based on this one, we need to analyze the how much amount of instantaneous voltage taken by the resistor, and based on that, how much amount of instantaneous current driven by the same, and also the how much amount of instantaneous power taken by the resistor, and as well as so what's the phase angle taken place between the voltage and current of this resistor. So these so many things we need to analyze it in this concept. And the overview of the session means we need to discuss about the instantaneous voltage, what is the instantaneous current, what is instantaneous voltage and what is instantaneous current, and after that, based on that, how much amount of instantaneous power taken by the resistor in a complete cycle, and after that, how much amount of average power taken by the resistor also we have discussed. So based on the instantaneous voltage and instantaneous current, so we need to plot the phasor diagram representation, and after that, so what is the relationship between the voltage and current, and how we will get the average power value. Based on that, how we are going to perform or how we are going to draw the power curve of the whole resistor. So these things we need to cover in this session. Let's begin the session. So let us consider resistance of R ohms, and we would like to apply the sinusoidal voltage to the resistor. So that voltage is a V equal to then Vm sin omega t. So let us apply. Take a resistor, then need to connect to an alternative source. This is the AC source. So this alternative source has to drive some current is small I. So that is instantaneous current only. So this voltage. So let us apply the voltage. Let us apply the voltage of V. So that V equal to Vm sin omega t. So this is the equation number 1. So due to the applied voltage, there will be current circulating to the resistance of the circuit. So the current is determined with the help of the Ohm's law. So from Ohm's law, the current small I will be then I equal to according to Ohm's law V by R. So means we would like to get the instantaneous current means instantaneous voltage upon the resistance of the circuit. So that is I equal to V by R. So need to substitute the current value. So with the help of the equation number 1. So the V value is a Vm then sin omega t upon R. Vm sin omega t upon R. So need to write finally the I equal to it's a Vm upon R sin omega t. Yeah, Vm upon R into sin omega t. This is the equation number 1. So if you are applying, if you are able to apply the instantaneous voltage like V equal to Vm sin omega t, then current also will get in terms of the I equal to Im sin omega t. Means, but we have got this value as according to this procedure, we got the I value is Vm upon R into sin omega t. So this I value, will be maximum. So this I value will be maximum at. This I value will be maximum at omega t equal to 90 degrees, or other words we can say sin of omega t is unity. So at what time we will get I as I max means, so whenever we got the omega t equal to 90 or omega t equal to 90, or we can say the sin of omega t function as unity, then we'll get the whole thing will become means the I value will become maximum. So therefore I equal to, according to the statement, so Vm by R. So this one is a maximum means then the corresponding value we will get in terms of the maximum I max. So therefore I equal to I max equal to, it is a Vm upon R. I max equal to simply Vm upon R. So the same value we will like to substitute in equation number 2. So therefore the final instantaneous current circulating to the resistance of the circuit, resistive circuit due to the applied voltage, that is I equal to Im sin omega t. So this much amount of current is circulating to the resistor. So this is the equation number 3. So based on the equation number 1 and 3, we need to draw the that is a voltage and current waveforms of the network. So this is the voltage waveform, starts from 0 and also reach the pi, and again need to consider the one complete cycle. So within the span of 2 pi radius, otherwise. Then after that, current also. So there is no angular displacement between the voltage and current of system. Here the voltage and this one is the current. So there is no angular displacement between the voltage and current. So the current also start with the again 0 with respect to the with respect to the voltage. Current also start with the same point or same notation only. So that's why. So this is the voltage and, or we can say, the waveform notation of our representation of the voltage and current of the resistor. So whatever the voltage applied to the, or whatever the shape or whatever the symmetry maintained by the voltage, and same symmetry followed by the current. So because it's a driving force of that, that's why we can write the we can draw the voltage and current waveforms of the system, or any circuit, or any this resistor circuit will be like this. So this is a voltage, instantaneous voltage value, and this is the instantaneous current value. So this one is only, we can say here written as a IM into R. So otherwise also we can write it as a VM. So VM sin omega t also we can consider. So based on the Ohm's law, we have expanded that here. That's why VM equal to IM into R we got. So from this one, need to draw the phasor diagram. So it's a easy way of representing the voltage and currents of the network, or any circuit or any system. That's why we can adapt to the phasor representation. So to draw the phasor diagram, need to consider the voltage vector as a reference. This is the V. So with reference to the voltage, both are, we can consider the RMS values only. That's why. So voltage is a reference. With reference to the voltage, current is always so within the same phase. I mean, both are in phase. Both are in the same phase. So that the corresponding phase angle should be, it is a 0 only. I mean to say, the power factor of this kind of system should be, or this kind of circuit should be, that is a cos 0 equal to 1. I mean unity. So if it is a pure resistive circuit, the power factor should be unity. That's why. So this is a pure resistive network case. So this is the voltage and current we got till now, and also power factor. So from the phasor diagram, we have clearly conclude that the voltage and currents are in the same phase. Also the waveform notation, the voltage and currents are in the same phase. There is no phase displacement, or there is no phase delay. So this is about the voltage and currents. Then after that, we need to consider the instantaneous power. Then the instantaneous power consumed by instantaneous power consumed by resistor. It is an instantaneous power. So the instantaneous power is a P equal to V into I. That means instantaneous voltage and current. So here V is the Vm sin omega t from equation number 1. Then I is the Im sin omega t from equation number 2. Sorry, equation number 3. So based on this one, we will get a Vm, then Im sin omega t. I mean sin square omega t. Both are sin omega, so that we'll get sin square omega t. So need to multiply the 2 here. We will get simply write this. So sin square omega t means some 1 minus cos 2 omega t by 2. We can write this one. So then simplify, after simplification of this term, we will get P equal to, that is a Vm Im by 2. It is a Vm Im cos then 2 omega t by 2. So this is the instantaneous power taken by the resistor. So this is the instantaneous power taken by the resistor, that is a Vm Im by 2, Vm Im cos 2 omega t by 2. So based on this one, need to find the average value consumption of the resistor. The average power taken. The average power consumed by the resistor over a complete cycle. Over a complete cycle should be, so that is the P average equals to the 0 to 2 pi. Need to consider one complete cycle, that is a Vm Im cos 2 omega t divided by 2 into d omega t. I mean to say, why should I consider only this term means the instantaneous power having the two parts. One is a constant part, other one is a variable part. So the variable part appeared with the cosine function with the double frequency. The variable part of the instantaneous power appeared with the help of the uh, cosine function or sine function. I mean to say the cosine function here we got. So the average power consumed the resistor in a complete one cycle. So that should be treated as simply 0 means. So the instantaneous power consists of the two parts. One is a constant and variable. So the variable term is existed with the cosine function. So the cosine function with the double frequency, the average value should become 0 means the variable part of the instantaneous power should become 0 means it's a cosine function with the double frequency. Hence the average power taken by the whole resistor should be. So the average power resistor taken from the complete cycle, that is Vm Im by 2. So which means Vm by root 2 into Im by root 2. Vm by root 2 into Im by root 2. So therefore, over a complete cycle, the average power taken by the pure resistor from the alternating source is the Vrms into Irms. So this is the average power taken by the pure resistor. So this part has 0. I mean this part constant means there is no zero term here. That's why. So this value simplification. So we need to do with the help of Vm by 2, Vm by root 2 and Im by root 2. So based on that one, we got it as the average power consumed by the resistor over a complete cycle should be equal to Vrms into Irms. So about this part means, so this variable part of the instant power, so we will get 0 because the average value of that one is, so with the double frequency should become 0. Based on that, the average value of the resistor should be equal to, so Vrms into Irms. The next one we need to draw the phasor diagram and power curves of the voltage, current and power. So phasor diagram we have already seen, we have already discussed in the second slide beginning of the session. So this is the phasor diagram with reference to the voltage. Here we have considered the peak values. So peak values or RMS values, both we will get same thing only. So based on that one, voltage and current of the particular network should be in phase, same phase only. So there is no phase delay. That's why the phase angle should become also 0. So based on that one, we need to plot the voltage, current, power waveform. So this is the, so this blue one is a voltage waveform. So start from 0 and reach the peak value and also so end by 0 like this. This is the voltage. So current also maintain the same symmetry, so that it also starts from the again 0 only. There is no phase angle and there is no phase displacement between these two. So based on that one, we will get the same thing only. So this is the instantaneous power. Sorry, this is the average power. So average power taken by the resistor should be, so Vrms into Irms. RMS means, so we need to do the squaring of signal, then only we will get the average value. So based on that, either the current or voltage, the average value should become this one only. I mean double of the voltage or current cycle. So here also double of the voltage and current cycle like this. So it is a 1, then this one is a double. Here also 1, then this one is a double. Negative means square of the negative means positive only. So that the power should be always positive only. This for only complete cycle. So need to consider the other means we'll get also same thing only. This is the power of the other cycle. I mean other half cycle. Also power of the one more half cycle. Like this we will get. So it is the squaring of the, so this one. And the summary of the session means, so we have analyzed the resistance of the any material or anything with the help of the AC source. So by that we need to get the instantaneous voltage value. Instantaneous voltage is the applied voltage, that is V equal to, so Vm sin omega t. Then based on that one, so we'll get some current, that is Im sin omega t. So based on this one, we'll get the instantaneous power is that is a Vm Im by 2, Vm Im by 2, and also the Vm Im by 2 cos 2 omega t. So this is the instantaneous power taken by the resistor. So in the instantaneous power, we have the two parts. One is a constant, other one is a variable. So in the constant parts, there is no variable. I mean there is no change in this constant value. I mean there is no change in this constant term. So in the instantaneous power, there will be a changes according the variable term, because it's vary with respect to the time. That's why. So need to change the or need to vary this value of the instantaneous power. So it is appeared with the help of the cosine function or any sine function is appeared. So the whole term average value should become 0. So therefore the average value taken by the resistor should be, it's a Vm Im by 2 or Vrms into Irms. So after that also we have draw the power curve and also the phasor representation of the voltage and current. So this is the power curve we have already drawn in the last slide. That is, this is the voltage and this one is the current. Both are in same phase. There is no phase displacement. So this is the power curve. So it is the RMS value of the power curve. That means it is a P and this one is a V and this one is a current. So this is the parameters of the resistance, that is a voltage, current, power factor and also the phase angle. So these many things we have considered in case of the pure resistor with the help of the alternating source. So this is the end of the analysis of the resistor network with the help of AC source. So thank you and all for this session. So in the next session we would like to discuss about the analysis of the pure inductor with the help of AC source. So thank you and all. Thanks for watching.